We've completed our static model, and now we can start to look at making some things a little more dynamic and add some detail. So under the configurations, we're going to be able to expand that out and add a configuration. And I would like to have one that is dynamic, meaning that it can move. And we're going to go back and find a couple of those mates that allowed this to um, stay in place. So if I go to the complete mates, let's look at the distance. So the distance would be one that I want to suppress, and as this moves, we're going to be able to see it go back and forth. So if I wanted this to turn, we have a 5/16 18. So let's pick the outside just in case it drops into the mate. And we'll go to a mechanical mate, look at the screw. Revolutions per inch is 18. And we should be looking at that one. And we'll go ahead and accept. All right, so now, so that went back fully defined. Okay, so let's look through the mates. And oh, we have a lock rotation, so it can't move if we can't if the rotation is locked. So we're not really going to see that. I kind of get the hint that it's spinning, but maybe if we turn on the origins, as this moves, you'll see the origin spin and indicate that movement. All right, so the other thing then is as we turn this, it would act as a spinning. So one of the things we could do then is look at going into a collision. So if I move the components and just select the slotted washer and the face, resume the drag. And that is, oh, stop at collision. And we got a few more things in there than I wanted, so let's make sure we select those again. And resume drag. Okay, so there it is at a stopping point. So that would be the maximum distance. And we'll get a distance of 0.94. So if I go into the mate, and it's going to default to coincident, then we would look at the advanced mates and go to a distance, and the distance is going to show, all right, well, the 936 is rounded, so I don't know that it has to be that precise, but minimum then is going from, let's just make it 0 and see what that looks like. So we'll go from that face to that face, and we're not quite running off of the end of the nut yet, so let's go ahead and do one more. So the screw then will expand it out. I'll go ahead and unlock the rotation first on this one. So we have the concentric, the coincident, and if I suppress the coincident, that is going to allow this to move up and down. Okay, and I want to keep those because in the static or the default, we want to be able to return to a known position, or if we do any detailing in our drawing, that we would be able to make sure that it doesn't do anything strange between the two. All right, so let's clear the selection there. Make sure that I have the two faces. We'll go to the mechanical. Again, revolutions per inch is 18. If we need distance per revolution, we would do 1 divided by 18, which works out to 0.0556, let's just say, for the round. And we'll go ahead and accept it, And let's see, that actually looks like it's going backwards. All right, so I should be turning this clockwise to engage and counterclocking to disengage. So let's edit the feature one more time, and we'll turn off the reverse. All right, so the downside then is that I have to either spin this a bunch of times to get it back in, or temporarily suppress the mate so I can engage it, and then unsuppress it so that I can activate it. So that gives us some movement to work with on our dynamic configuration. Then we'll go back to the default. Don't have any errors that it messed up. So let's see, that one went to a minus. So I'm not sure if I can lock the rotation on that concentric for just this view. I haven't really tried that before. So maybe in this configuration we add a parallel, and then if I go back to the dynamic, the parallel can be suppressed. And we would probably want to put a limit mate on that because it will keep going into, it'll keep going into the body. So we're going to use combinations of those mates to help us define the movements that we want to see. So let's go back into the mates. And so the parallel does get suppressed. I'll have to look into that lock rotation. All right, so if I select Control Select, and let's just go into the mate and to the advanced and the distance, then the minimum. Oh, let's see, we're at 0.5. So the minimum will be 0, and the maximum, say, will be 0.75. Okay, and the we'll let it catch up. All right, so it stops, and then we can unsuppress the mate so that we can turn it and see what it activates. But that way it doesn't go into the body of our part. All right, so let's go ahead and leave that in the default. Don't have any errors going for the mates or any conflicts that I created. So the adjusting, probably going to be the same thing. Let's go ahead and check out the lock rotation. And if I go back to dynamic, yeah, see everything's back to being fully defined. So there again, we would need to find some geometry to allow us to keep that that rotation unlocked. Go back to the dynamic. All right, so everything's able to move, and we can adjust as needed. All right, so I'm going to stay in the default. So on the manufacturing side, our design for manufacture, this was maybe created in the, well, a long time ago when cast iron and casting processes were a kind of our primary production method. So having the rounded corners, those kind of came in with the sand casting or whatever method was doing. If I was going to machine one of these, I would probably put it in this orientation. And so doing that, these radiuses become a little more problematic because the round over tool and going into steel, or doing a little 3-axis across there takes time, and of course that adds cost. So one of the things we'd want to look at doing with our configuration then is add a configuration, and let's just make one for manufacturing process. And so everything else is is pretty good. The fillet, then we added everything. So on this one we can suppress it, and so going this way I would look at maybe only having the radiuses at the top. Now at the bottom, these would more than likely be sharps or at least minor edge breaks. So the typical rule would be that we wouldn't put a chamfer in unless we wanted a certain size, and it wasn't just to deburr, break the edge on the part. So let's look at this as if so the reason I'm going to a chamfer is that putting a 45-degree tool and knocking that corner off it requires less precision, requires less blend than the radius. In this orientation, the tool is coming around this way, and it's just naturally generating those radiuses because I'm probably going to be moving that material, drilling and tapping. When I set it up on end, I could potentially go around those corners, but then we still have to do the blend. So I want to minimize the setups in the machine and do something that will look good, make the sharp edges not so sharp, and so something like that. And if we needed a little rounder, we could always take a file and kind of knock those edges off. But we're really trying to get this to come off of the machine in a way that doesn't have to be further modified. All right, so the back side, I don't really have any operations on this side. If I were going through the process, I would probably start with a piece of material that was a little thicker, run all the way around, and have the tool generate this this geometry, create the pocket, and then set it up on end. Go ahead and drill, machine off the face, put in the reliefs, and then on this side, that hole would probably be drilled through. Let's see, we're 4 inches. That's a little bit long for a standard size drill, but we could get through, and then drill and tap the other 2 holes. Should be able to drill and tap from that side. So when I flip this over, really all I'm doing is facing off whatever material I was holding on to. Let's see, because of the thickness, we're looking at standard size 2.063, so I would probably be looking at 2¼ inch material to be able to remove that that face. So thinking through manufacturing processes, more just so you hear the terminology and kind of go through the understand the machinist thinking of how am I actually going to create this. Of course, if we were 3D printing one, I don't know that I would put a whole lot of load on this, but if we were 3D printing one of these items, then a lot of that doesn't really matter. It just becomes orientation and support. So I'd probably still 3D print it from this direction and have some supports on that side for the geometry. So the other thing that would be a concern is if we were putting a lot of load on this, we would want to identify on the engineering side, we'd want to identify our stress risers. So this edge and this edge being a 90-degree sharp are part of the manufacturing. And if we're putting a lot of, let's see, this would be as we turn the screw down onto whatever tool holder. Let's go back to the, okay, so whatever tool holder we put in here, as we're pushing this down, the stress on this little overhang is going to be in tension, pulling that way, and then this will be pushing down. So it'll be more of a compressive force that we're having to deal with. But those two stress risers, then, if and especially in a material that is cast, that would be somewhere where we'd want to consider putting a minimal radius, just to make sure that we're increasing the strength across that face. But then that means that this piece would have to have a matching radius to be able to slide smoothly and not create a gap or a twist in that shape. Mentioned when we were doing the bolt that there's probably better methods to do this, and because of the different sizes of carriage, right? So this is going to fit into the compound, rest on a lathe or other machine, but there's going to be different sizes depending on the manufacturer. So these were 1 inch by 1 inch. We'd really want to consider this, consider the possibility that this would be everything from, well, we had a 1/2 inch, maybe up to 1 1/4, 1 1/2, depending on the geometry. So rather than machining this out of a square stock, which is just a lot of machining, a lot of setup, we would do the possibility that we could, if I edit the feature, and that brings us to size. So that end had a 1/2 inch. So yeah, we went to the 5/16. So let's go ahead and edit the sketch, and we'll put in. All right. So our choices are, we could, let's see, that was a 1/2-13. So we're looking at 421, I believe. So let's go 421 would be the tap drill. All right, so I could put that in after. Let's see, that is merged. So in my what if scenario, now I have a situation where I can say we can have different size bodies on the base, and I don't really have to create a separate assembly or separate parts at this point, because this is concept. We would want to be able to illustrate how it works, or why we've gone down this decision path. So the other thing we might do is if let's go back in and edit the sketch. So I can always turn that to construction geometry, and since we've managed the merge, then let's do a rollback so it's kind of in sequence. And I would want to see if we can get it to rotate over here. Go into the hole wizard, and we're going to put in a 1/2-13. So this is automatically going to generate our cosmetic thread. And let's see, did I guess right? 257. Oh, I didn't. I'm still in the 5/16. Let's go up to 1/2-13. All right, 1/2-13. And 422, so close enough. All right, so this gets the cosmetic thread. As we roll forward, then now we have a potential where we can see how those two interface. And if we do decide that we want to just make a bunch of these little blanks, thread this in, to actually fit this, we could maybe stop the thread a little bit short, so there's a where it doesn't complete, so this would the shaft would run down and seat on it. We could do a chemical, like a red Loctite, so that it didn't spin out. If this isn't going to take a lot of load, I might just take a punch and peen a few little spots on the intersection of the shaft. And if I never wanted it to never come apart, then I would leave this little shy and put a weld bead and then grind it flush. So those are kind of the manufacturing options we need to think about as we go through the process. All right, so let's see what kind of I mentioned actually generating a knurl. I've tried this several ways, and typically I'm 3D printing. If this is going to be a machined part where the knurling tool is going to press the diamond shape in or the straight shape in to the face, all I need to do is call it out and maybe show it. But 3D printing, then I would actually want to be able to generate this knurl. So let's go ahead and go past the chamfer, and actually I think the chamfer is going to disappear. We'll see what it does. So I've had the best luck with a lofted knurl shape. So to start the loft, I need a curve that will follow this the cylinder around the part. So let me get back into that view. I'll go into the right plane. Okay, close enough. And start a sketch. And we just have to determine what the angle of our knurl is. So if I put a center line between that point, then I can pick the midpoint, go to the midpoint, and let's see how close we are. So 45 degree, that's quite a bit. So let's see what a 20 degree would look like. So I don't want the twist and the blend to get so crazy that it kind of loses that diamond pattern. So let's go ahead with that. And then to actually get that curve onto the cylinder, we are going to go to the curves tool, which we haven't used before, and we're going to project that curve onto sketch onto faces. And let's see, we have a direction, and then we have the face, and so we see the curve is generated there. All right, so that gives me some geometry to work with. And so if I open up a sketch on this face, then I'm going to want now let's go ahead and this is going to be, might let me do a coincident, but now since it's not showing me the coincident, I'm going to pick the curve and go to a pierce. And then we'll switch that over to, there we go. Yeah, we'll see what 60 looks like. It's probably a little deep. Make sure that that is horizontal. Oh, let's go Control 8. All right, so that looks better. Yeah, I'm thinking 60, but let's go ahead and exaggerate it and see what we end up with. And we'll merge those 2 points, or coincident them. Let's go ahead and give it some symmetry. And then our angle, let's go with like a 60 degree. 90 degrees probably better. Definitely a lot wider. All right, but this is just a concept at this point, so let's give it like 20 thousandths just so everything is there. Now if I window pick this and do a Control C and then accept, I should be able to open a sketch on the bottom and do a Control V. So everything came in, but it's 180 degrees out, so I need to rotate that. We're going to go into the rotate operation. We'll just give it a center of rotation and tell it it's 180 degrees and go ahead and accept. So we haven't lost anything at this point. And I'm going to take my center line and make it pierce that edge, and we're going to see what else we need. So the center line going horizontal, that gives me my geometry. All right, so we're ready to do a lofted cut, and the lofted cut will be between the two sketches. And we need a guide curve because right now it's kind of twisted, and that curve that we generated will force it to follow the shape. So that looks like it offset it. Alright, so it doesn't look like it got my curve, or I didn't select it, so let's make sure I'm actually selecting. No, it did curve 1. So what happens if we change the connection point? Because these are the default grips. And it's following the curve. Okay, so I think since I made the sketch horizontal, let's go ahead and get rid of that. I removed the horizontal and the vertical and made this perpendicular to that, to my center line. So let's just go ahead and make those coincident because it's telling me it's not intersecting. Alright, so let's go ahead and edit sketch 6. Alright, so I'm going to go ahead and remove that one. This did not come in with a vertical, but this comes in with a horizontal. So I do want to keep those perpendicular so it kind of stays tangent. All right, so we'll go coincident, and then I can select for coincident and see if that updates the check. So it's been a little while since I've done one of the lofted cuts, so let's go ahead and see what we get with this. Alright, so now I got a preview, so I don't think it liked my gap. And so that was kind of the concern with the other is, alright, so it did leave a little sliver. So I think that has to do with the depth, but let's go ahead and edit it. See if it lets me have access to the bodies. Should just be looking at body 1. Alright, so this is going to be a really deep knurl with that geometry. So let's go ahead with the cut and the right plane, and I'm going to mirror my my cut, so I have one opposite. Oh, that's nice. Let's see, propagate. So the cut loft, yeah, that's the feature. All right, so geometry pattern does a different kind of solve. All right, let's go ahead and see what this looks like if I do a circular pattern. And we just need a cylinder. And then we need enough of these that it starts to look like a knurl. So let's look at it from the in view. I think those are starting to come together. So let's just see what that looks like. And if it goes to geometry pattern again, well, that's a pretty heavy duty knurl. So it didn't cross over, but oh, that is kind of neat. So let's go ahead and increase it maybe to 40. All right, so we've got some diamonds in there. If I change my angles and change my my depth of cut, it will probably clear it out a little bit. But we go back into the chamfer. The chamfer can't find anything, so I'm going to go ahead and delete that that chamfer. If we want to take these sharp edges off, then we're going to be looking at a right plane. Actually, I think what I'll do instead is if we generate that angle before, we can kind of manage. So let's see, that would be the front plane. Nope, we'll be in the top plane. If I generate this angle before, I can use it later, but it will be tied to the pre-knurl, the pre-loft geometry. So we have a 45-degree chamfer, and we'll make it millimeter 40 deep. All right, so if I were to go equal on those is, nope, not parallel, equal. That should get me fully defined, and then we'll be center line, vertical, we'll just go infinite length. All right, when I roll forward then, after everything's in place, well, there's not much left, is there? Okay, usually I end up with some more. I think that's the 60 thousandths depth, but let's see if it cuts anything. All right, so just to illustrate the point, and I am kind of thinking about 3D printing one of those because it looks neat. All right, but that chamfer just knocks the tips off, where the chamfer tool won't pick those up. The revolve cut will. All right, so always an interesting result. Needs a little refinement, but gives you the idea of how to generate the loft. Let's see, we save that. We go back into our part. And now if I'm in the dynamic, all right, so change something somewhere. Yep, change something in the mate. So it's always going to be a refinement issue that we check and we double check. So that one has the rotation going on it, the adjusting nut. Let's see, we didn't put a parallel to override the concentric. So right plane, let's go right plane and top plane parallel. All right, so that'll make it fully static. And then in the dynamic, because something lost, probably lost the geometry. Oh, I picked the outside and then I cut the outside. So we're going to take that missing face and transfer it. I should have picked the inside anyway, but you can pick whatever geometry, but be aware that if you change the geometry that you're going to get those results. So now when we drag the wedge back and forth or we turn the knurl, you have a little more visual in the shape. So let's go ahead and save this, and there's certainly more items. I think I mentioned that I would probably, in a modern manufacturing, I would be looking at changing these over to a socketed cap screw, or looking at what square nuts were available for purchase rather than manufacturing these. I think we've got a pretty good start on our engineering process, so we'll call this one good here. So I made the changes on the tool post, but then we didn't activate it. So let's go ahead and just look at what it takes to change the the configuration. So I'm going to go to the manufacturing configuration. I'm going to make sure that it is only this configuration. So we look at it in the dynamic, then we'll have those chamfers and edge breaks. And then going back to the default, it changes back to the radiuses and the geometry. So since we're doing this, the display states is tied to the is independent, but I can tie the display state by going into its properties and link it to the configuration, so that when I'm in the default, we have all of the standard colors. If I go to dynamic, it switches to display state 2. And then we would be able to, within the configurations, if I just needed a highlighted color, I could change different display states. Or if I'm doing something more complicated, I usually make a work in progress display state so I can move things around, hide them, show them, and it gives us a little more functionality. So on this piece, we can go transparency, maybe make the wedge. Let's go to its appearance, and we will grab the assembly. So we want to apply at the component level. Let's see, I don't know if that's going to do both of them or just the one. Yeah, it looks like just the one. So on its appearance, we can copy the appearance and then we can paste the appearance. What else would be interesting? So don't usually go to the materials, but if we wanted the materials to show up in the drawing, then this would be the time where I'd want to go down through the tool post and let's see, we have edit material. Let's just go with the standard 1020, 1018, 1020. And this is going to start the process where we go down through all of these items and we set, I don't know, set some different colors. So I do not have the real view graphics on this computer, but the real view would also change the shininess, make one copper. Just I would never make it out of copper. Well, yeah, I would never make it out of copper. So let's just go to another steel, and then I was actually thinking about maybe the adjusting nut material. Let's make that one out of copper so it's a little shinier. All right, so where this comes into play is we've changed all of these. If I go back to the default, oh, that one didn't, and that one didn't. So apparently I didn't check the boxes, but doing the colors, well, actually the material is overwriting the colors on those, so that makes sense. The transparency and the color green, those are visual properties. The chamfer and the different changes we made, those are visual properties. So the configurations control physical and the display states control visuals. So I think we can wrap up here.